Good morning. This is your stats sensei, Mr. Spensei, and today we're going to go back and recall the binomial distribution. And I'm not going to spend a whole lot of time with that, but we're going to review that just a little bit. So we're going to use that to set us up to start running hypothesis tests for proportions. This is going to be very similar, or hypothesis tests for proportions is going to be very similar to what we've been doing. The formula is going to change, but the language is going to remain much the same. So real quickly, binomial distribution is a Bernoulli trial. Remember, Bernoulli is you have two possible outcomes, a success and a failure, which the probability of success is the same every time the experiment is conducted. So two possible outcomes, we say success is noted by P. I like to use failure as a Q, but if I do that, I have to tell you that Q is 1 minus P, all right? Because please remember they have to sum to 1. The probability of success, P, is constant, and the trials are independent, okay? And we have a fixed number of trials. No, when we don't have an infinite population, the trials really aren't independent. However, it's still okay to proceed as long as the sample is smaller than 10% of the population. Remember the M&Ms. We have a giant pile. It's huge and massive, and it's all the M&Ms that M&M Mars Company makes. We check and I eat one of them, technically the percentages change, but it changed so slightly, we don't worry about it. We say it's negligible. All right. So the binomial model gives us a probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. All right. Characteristics, two outcomes. Each trial is independent. The probability of success is constant, and the trials are independent. Please note, the number of trials are predetermined. We're saying, hey, we're going to do this out of 30 or out of 40 or out of 100 or even out of 1,000. We're not going to continue to the first. This is the overall formula. In choose, and a lot of times the formula chart, I think, shows it as in choose x, p to the x, and then it says 1 minus p. I like to use q, and this is just going to be n minus x. Okay. All right. The mean for the binomial is very easy. The mean or the expected value is just the sample size times the probability. Variance, the sample size times probability times 1 minus probability, or n times p times 1 minus p. I like to abbreviate this way. And the standard deviation is n times p times 1 minus p. And once again, I like to abbreviate with the q, just makes things easier. As a reminder, binomials are usually expressed, what is the probability of a certain number of successes in a given number of trials? And if it's a specific number of successes, then it's a PDF, because specific singular value is a point, it's probability of it happening and occurring in one place. What's the probability of no more than some number of successes? This is going to be multiple values is a CDF. And then, of course, when we have the at least, it's going to be a 1 minus, and anytime it's an at least problem or a more than or a greater than, it's going to be a 1 minus. So given a box, so suppose the probability of having a defective light bulb was 0.15. Given a box of 30 light bulbs, what's the probability that 2 are defective? Well, we have a specific number of defects, and essentially, in this case, we have 30 light bulbs. We could have 0 defects, 1 defect, 2 defects, 3 defects, 4, all the way up to 30. But I'm only interested in having one singular value. So what's the probability of having 2? Since I circled one value, this is telling me that it's going to be a binomial PDF. And I'll set my formula up. 30 choose 2, 0.15 second. Now 30 minus 2 gives me 28. And then this value, obviously, I have some sort of typo here. This should not be 0.7. This should be 0.85. Let's scratch that out. All right. And here we go. Second vars. Binomial. And by the way, let me remind you how to get there. Second, followed by the vars button, which is right here. Really, it's distributions. We're going to scroll all the way till we get to binomial PDF. We have 30. Our probability of success is 0.5, and we want to have 2 successes. By the way, these must be whole numbers, all right? When I do that, I end up getting that probability is 0.1003. Next thing, given the box of 30 light bulbs, is probability that no more than 2 are defective. So in this case, I have this. I have 0, 1, 2, 3, 4, ... all the way to 30, but no more than 2 means 2 or less. Notice I circled multiple values. Because I circled multiple values, this is going to be a CDF, and I'm going to have to show my work going, starting with the lowest all the way up to the highest one of interest. So 30 choose 0, 0.15 to the 0, 0.85 to the 30th. Then I can do 30 choose 1, etc. But I can shorten my work by just saying plus ... plus. And so in this case, second vars, binomial, CDF, trials is 30, probability is 0.15. And notice I'm using the exact same thing, but I went to the CDF, which is cumulative, because it summed everything up. So this summed up those values and we get 15%, all right? Given a box of 30 light bulbs, there's a probability that at least 28 are not defective, all right? So this is tricky. First off, the probability of not defective is going to be 1 minus 0.15, which is 0.85. So the probability of not defective is 0.85. Now, we have 30 bulbs, so 0, 1, 2, 3, ... 27, 28, 29, and 30. And I want at least 28. So that means I want these 3 values. Okay, so those are the 3 values I want. So my work is going to be the sum of those 3 values. 30 choose 20, 30 choose 28, 0.85 to the 28, 0.15 squared, because 30 minus 28 is that. Then I skip to the highest one, 30 choose 30. And so that would be my work shown. To run this in the calculator, we didn't circle 0. If you don't circle 0 and you're working with a cumulative, you're going to need to do a 1 minus. So 1 minus, second vars, binomial, CDF, 30, my p-value is 0.85, and then what do we subtract? Well, we don't subtract out what we want, we subtract out the highest value we don't want. And the highest value we don't want is 27. So basically, in this case, it summed up every single value up to 27, did all of those, and then brought it out. Now, where did the 1 come from? 1 came from the probability of, if I had circled all of the values and did a binomial CDF of 30, that would have been the probability of everything happening. So we took everything that could happen, every combination, which sums to 1, and then we subtracted out what we didn't want, which was anything 27 or below. All right, so that leads us into the normal approximation of the binomial. Once again, we have 2 possible outcomes, success and failure. And we have some restrictions on when we can use the normal approximation of the binomial. Very easy. Basically, we have to test to see if it's big enough. All right. So NP, our sample size times the probability has to be greater than 10. So the number of successes has to be greater than 10. And the number of failures, NQ, or N times 1 minus P, also must be greater than or equal to 10. So the number of successes and the number of failures must be greater than 10. So the best way is to look at what happens with the binomial distribution. So consider this. This first row here is working with sample sizes of 10 with different probabilities. When I have a sample size 10 with a probability of 0.2, I end up with a distribution that is skewed right. Matter of fact, we can say that if the probability is less than 0.5, the binomial will be skewed to the right. So probability less than 0.5, the binomial is skewed to the right. Over here at 0.8, we have a probability that is greater than 0.5, and we find that it's skewed to the left. So probability greater than 0.5, skewed left. Probability less than 0.5, skewed right. And if we have a probability of 0.5, it ends up being symmetric. So probability is 0.5, we end up with symmetric. That is something you need to memorize. So less than 0.5 skewed right. And basically we can sit there and go, well, 10 times 0.2, what would we expect? We'd expect to be centered on 2. All right, our expected value in this case would be expected is 10 times 0.2, which equals 2. Here, we expect to be centered because 10 times 0.5 is 5. 10 times 0.8 is 8. So that's how we get those centers. Now, based on this, and by the way, this is symmetric. Just because it's symmetric does not make it normal. And in fact, this is not normal, at least not yet. All right. But it is well, it's reasonably normal. All right. Based on these values, it would appear that the distribution is symmetric only if p is 0.5. But actually isn't true. What happens when we increase our sample size? So I'm going to increase my sample size. Up here we had a sample size of 10, but I'm going to increase it to 20. And I'm going to use the 0.8, which is skewed left. Well, if I do that, I go 20 times 0.8 and I get 0.16 or equals 16. So we're centered here at 16, but I can still sit there and go, you know what, this still has some skewness. All right. And my failures is 20 times 0.2 is 4. So this satisfied NP greater than or equal to 10, that was satisfied. But NQ greater than or equal to 10, that was not satisfied. But I go over to here, and now I've increased my sample size to 50. And I look at this, and I go, gosh, that's reasonably normal. All right? It's not perfect, and it never will be. It just starts to approximate. And that's why we call it the approximation, normal approximation. It's not exact, but it's close enough that we're okay with it. So 50 times 0.8 equals 40. And that's greater than or equal to 10. And 50 times 0.2 is, the 0.2 came from 1 minus that. So NQ is also greater than or equal to 10. So that was also satisfied. So we are just barely large enough to use the normal approximation. So in this case, the normal approximation is appropriate. It's not appropriate here. NQ wasn't big enough. Remember, both NP and NQ, both must be greater than 10. So basically, this is a way of saying central limit theorem. So central limit theorem for means states that the sampling distribution of expected values of a population with a mean of mu and standard deviation will always be approximately normal, regardless of the shape of the underlying population, if the sample is large enough. And that's basically what we're saying with the binomial. If the sample size is large enough, the distribution of the proportions or p hats will also be approximately normal. So remember, with central limit theorem, we're working with not the individual values, we're working with the distribution of the sample means. And we say the distribution of the x bars is approximately normal if n is big enough, which is greater than or equal to 30. All right. So now we're going to work with central limit theorem for proportions. All right. Once again, it has to be large enough. And we have a few number of conditions. Well, random sample. Well, that's not unusual. N is less than 10% of the population. Once again, it's the same thing we've always had. The degree of dependence is minimal, relatively independent. You know, remember, we're sampling without replacement. We have the giant pile of M&Ms. We're taking one away. Percentages are technically changing, but only doing so slightly, so the impact is minimal or small. And then we have to be large enough. So NP has to be greater than 10, and NQ is also greater than 10. Notice I used P hat and Q hat. Basically, that means from our sample. The hats represent from the sample. P and Q are from the population. I like to call these the Goldilocks. All right. This is not too big, and this is big enough. In other words, things have to be just right. Well, when we were working with a z, we had this formula, x bar minus mu sigma divided by the square root of n, where that was the sample mean and that was the population. Well, here, this is the sample proportion and that's the population proportion. And before we had a standard deviation divided by the square root of n, where that was standard deviation of the population. Here we're going to have PQ divided by the square root of n. And there's going to be some changes to that in a moment. Here we have T equals X bar minus mu S divided by the square root of n if we're using standard deviation of the sample. Well, that maps to this. What maps directly to this is Z equals, and by the way, proportions are going to be Z test, P hat minus P square root of P hat Q hat over N. So essentially the same thing, but here we're using the sample, here we're using the population. We'll use the population if it's known, but most of the time it's not, all right? So where does P hat come from? X is the number of observed successes and the N is the sample size. So the standard deviation, we talked about mu, the standard deviation of X bar. Now we're talking about the standard deviation of P. Standard deviation of P, PQ divided by N. And if we're working with the sample, P hat, Q hat divided by N. So here we go. Assume that 27% of the students at Reagan wear contacts or other corrective eyewear, and assume that we randomly select a sample of 110 students. What is the distribution of P hat? Specify the name of the distribution, the name and standard deviation, verify all conditions. How the distribution is normal because we're working, the distribution is binomial because we're working with proportions and we have a fixed number of trials and we have a fixed probability. All right. But we could use a normal approximation because NP is 29.7 and NQ is that's not 29.7, is 80.3, which is also greater than 10. So both of these are greater than 10. So we're okay to use the normal approximation. All right. So our expected value, our mean, our population mean would be 0.27. This is what we expect to get. And our standard deviation would be 0.27 times 0.73. This 0.73 is 1 minus, and we end up getting this value. What's the probability that more than 30% of the sample use corrective eyewear? Well, technically, I could have done, 30% of 110, 0.3 times 110. So I want the probability that more than 33, and I could sit there and go, you know what, 0, 1, 2, 3, ... 32, 33, 34, all the way up to ... 110. And I can run this as a binomial. And I could do that. However, we're going to find that it's going to be necessary to switch over to the normal approximation. So let's do it this way. So our formula is P hat minus P, then PQ divided by the square root of N. Well, the population happens to be 27%. That's our claim. But we want to know what's the probability that we get a P hat of this. If you know the population, you must use it. If you know the population, you must use it. All right. So we can go to what is known as, so we're going to stat test, and we can do a one proportion Z test. Well, the claim is that it's 0.27. Our X, well, we want to have 30 or we want to have 30% or more. So we can go 0.3 times 110. Be very careful. This must be a whole number. Must be a whole number. If it's not, you're going to have to round up or round down. The choice will be yours, but X must be a whole number. If not, it's going to kick it back to you as an error and you're going to get very nervous. Greater than, because that's what we said. We wanted greater than that. And we end up getting 0.7087 is our z-score, and 0.239 is our p-value. So we could do it fairly easily, I think much easier than running a binomial. So that's the normal approximation. And we're going to do some, this will be the intro, and we'll do some other problems with it here in a moment, all right, with the next video. So thank you for watching.